Okay. In English, right?
Yeah, in English.
Okay, so good afternoon, everyone. I'm going to present very quickly this paper, Research for Light Dark Matter with NA64 at CERN. So it basically, so the NA64 experiment is an experiment at CERN that collides a beam of electrons to a target, to an active target. And it uses a beam produced by the SPS accelerator. So in this paper, they try to probe, to study more the dark photon as a mediator of dark matter. So it's not the dark matter particle, it's just the mediator. And the NA64, it's good to search for the light dark matter, that is dark matter in the sub GeV scale, in the less than 100 GeV per se. So it's a bit of an experimentalist paper. So it explains a lot about the upgrades that they did and the in each component. But I mean, we are not so much experimentalists, so I'm going to talk about the general purpose. So they look for a dark photon um, in the using missing energy techniques that that participates in two processes. So dark photon produced by a hard Bremsstrahlung when the electron hits the target, that is the nuclei, like in this image here. It's a scattering between the electron and the nuclei in the target, or a dark photon produced in a resonant annihilation, and that occurs when the mass of the dark photon it's fairly the mass of the muon. So this dark photon, it's called this way because it's a boson, a vectorial boson that comes from a U1 group, just like the photon, but in this case it's massive, so this symmetry is broken, and this U1 is added to the standard model. It's called D because dark. So this dark photon has a mixing with the photon through this Lagrangian. Yes, Lagrangian that results in the kinetic mixing term, that is this epsilon. And this epsilon is what they constrain. So they say that you have two possibilities for this dark photon. You can have this dark photon being the lightest state of the dark sector, which would mean that it would mostly decay into visible states, into standard model particles. Or you can have a dark photon that is more massive than the dark matter, and this will result that the dark photon decays mostly in the dark matter. So this is the case that we are dealing with. I think they tell later that this dark photon is approximately 3 times the mass of the dark matter. So sorry. Yeah. So here they show the structure of the NA64 experiment. So you have this part that is the some trackers. This is the scintillator. This is where the beam comes from, where it's produced. These trackers are just to tell the the path of the electron beam. These both are magnetic dipoles that deflect the beam, which produce synchrotron radiation that you have a detector here, synchrotron radiation. You have here more trackers to track the beam, and you have this ECOL that is the calorimeter, and that is the target, actually. So the electrons hit here and produces a Bremsstrahlung, producing a dark photon, or a resonant process that produces a dark photon that decays in dark matter. This calorimeter also gets the energy of the electron, and this other ones, this HCOL, gets the energy of hadrons. So it's a calorimeter for hadrons. So with this, they set some conditions to get less background as possible. It's basically in the energy saying, okay, the beam that we receive is 100 GeV electrons, so we are expecting an energy that's maximal energy that's measured of 100 GeV. You have some conditions on the angle. If you have an angle, a deflected angle, smaller than a quantity, you don't count that it's deflected at all, because you can't do this differentiation, and so on. It's basically some conditions to reduce the background. Here you have a plot that shows the plane of the energy that you get in the hadron's calorimeter and the energy you have in the electron one. Mostly is in this region. The sum of these two energies must be 100, more or less 10 GeV. That is the total energy. And this area, this shaded area right here, I don't know if, yeah, the shaded area would be the area that if you have an event here, it would be a signal. So a signal for the dark photon. That is, you should have the less energy possible in the hadronic, and just in the electric calorimeter, and you just identify the signal if you have a missing energy of at least 50 GeV. That's why it's 0 to 50 or 47 here. So this is the area that you would detect the signal. This A, B, and C are areas that you use to measure the background. That's basically it. And they tell a lot about the upgrades and the mechanisms and so on. And you have this plot here that they use the Gen4 to produce. They use the Gen4 to produce this one, that is the kinetic mixing, in function of the mass of the dark photon. So you can see here, you have some other experiments like Babar and other ones, NA62, and you can see that in this region of mass, then in NA64, it's really constraining. These are excluded areas. And this peak right here, that it depends on the fermion, let me resume, depends on the fermion or scalar, and this coupling. This alpha is the coupling of a dark coupling, the dark photon and the dark matter. This right here is because of the resonant process that can occur. So it's roughly 0.1 GeV. That's more or less the mass of the moon. So yeah, with this plot, this results and these equations right here of these two parameters that are defined parameters. They don't have a name itself. It's this epsilon that depends on the coupling and the kinetic mixing, and the the ratio of the both masses of the dark matter and the dark photon. And this equation for the coupling, that depends on this F, which depends on the type of the dark matter, and it's a parameter that, I mean, they just say that depends on the mass ratio. So with both of these equations, they produce this final plots, which is the mass of the dark matter in relation to this epsilon, and the mass of the dark matter in relation to the coupling. So here the main conclusion of this paper is that, let me do a zoom, is that for the for standard values of this alpha, that is 0.1, and standard values of the dark matter mass, with the NA64 you can already probe the scalar relic dark matter and a Majorana relic dark matter. These dark matters are thermal dark matters, but it doesn't say much about the model. So this is our exclusion reasons. So you can already exclude a scalar relic with this coupling, and mostly exclude the Majorana relic, just with some areas that you can still have, but you can exclude this pseudo-Dirac fermion relic. With variations of the coupling, like 0.5, you exclude a little bit, but you still have a lot of areas to look for. And these peaks are, again, because of the resonance. So it's basically this graph is with the couplings, but the conclusions focus more on these graphs, because it shows the regions for the scalar and the Majorana. But it's using the equations that I showed before. And it's basically it.
Thank you. Leticia, can you explain, could you go up?
Yes.
Could you explain, yeah, that one.
This
So
one?
could you explain why when you go from alpha equal 0.1 to alpha equal 0.5, NA64 becomes less restrictive? As you see,
Yeah, because
in the left one, the bound, let's focus
Yes.
on n chi
Mhm.
equal to 10⁻3. Then we reach y equal to 10⁻13, right?
Yes.
So in the corner left, would you show everyone where I'm talking about?
The corner left.
Yeah, the corner left. The leftmost, yeah,
Yes.
that one you see. 10⁻13, that's the exclusion region for mass of 10⁻3, right?
Mm-hmm.
Yeah, point, yeah, okay. But now go to the right plot. When you have 10⁻33, the bound is 10⁻something, 10⁻12, 10 something, 10⁻13. So weakened, the limit weakened. Why is that?
I mean, through the equation, you can see more clearly, right? Because if you have a bigger coupling, yeah. So you have bigger values for epsilon for all these values.
Fine.
So it's understandable that it's less constraining. It is in this epsilon parameter.
Yeah. So why shouldn't we expect that the curves in black also, they go up? They would also go up. Why? Because they stay the same, right? So you see,
Yeah.
the black curves stay the same. We change alpha d, but the bounds weaken, but the curves stay the same. But if you could you go up to the relic density equation you explained before? Up. Yeah, no, that's Y. Go up, I think. Yeah, that one.
Okay.
So they're saying that alpha should have this value to produce the correct product density, right?
Yeah. It is. Let me just. Yeah, I think so. Is the definition for the dark coupling? So I think should agree.
Yeah, so I guess it's just because they are in the end changing what the dark photon mass should be to fit the right valence density. So go down. The plots. Down. No, up.
Here.
Yeah. Left. Put it. Yeah. See. So what they're doing in the end is, so they are changing what MA prime is to explain the right valence density. So yes, you said, so for instance, the y-axis, if you increase alpha d, obviously the curve, the limit goes up. Sure. But the theoretical lines for the valence density, which are the black lines, I was expecting them to go up again, also go up. Because if you change the coupling, if you increase the coupling, then the cross section, the abundance also changes.
Yeah.
But it's not changing because they are changing A prime. Somehow
Let me see.
because it does not change. Yeah,
In both cases, I think they consider.
They fix, right?
Yeah.
Oh, see, they fix this. Let's see. Okay, alpha D 0.1 left panel, alpha D 0.5 right panel, assuming. Could it go to the right? The right?
Yeah.
Assuming A prime equals 3 and U prime. Okay. Maybe that's the reason. Yeah, they're fixing the mass ratio, so.
Yeah.
Maybe when you fix it, you somehow the valence density won't change.
Yeah.
Okay, maybe I have to check. So because that's the thing that we want to do with NA64, you know, the one that we had the meeting about. So it's to, what we want is two things. We want to reproduce the black curves for that model, and we want them to produce the blue curve for NA64. So we're gonna do the black one, and they're gonna do the blue one.
Okay.
So one good thing would be to, at least for the valence density part, to see if you can reproduce, Leticia, the black curve. Because the black curve is just analytical expressions, right?
Yes. Yes.
So there's no differential equation to be solved. It's just analytical expressions and solved. They have a reference, then you have to go through the reference to understand better, but it's just analytical.
Okay.
Because then we can also play with this. Okay, if A prime over Mx is 5, is 6, is 7, is 0.1, where these curves go and so on, you know?
Yeah.
That would be nice. Because we can do that, changing the alpha D, changing the mass ratio. That would be nice to do. And then we can also ask Jacinto to compute how these black curves change if we invoke different cosmologies. Okay?
Okay.
But for instance, just so we can conclude now the meeting. For instance, let's say this curve perhaps is inaccessible to NA64, right? However, this is assuming thermal production.
Yes.
So if the universe had a different cosmology, such as a fasting, expanding universe, then the black curve rises up and goes around there. So you say then you can conclude, look, if the Astroparticles fermion is produced under non-thermal cosmology, will be within NA64 reach in the near future. Because this curve, instead of being here, will be right there. So now we can play beam dump experiments with cosmology within dark matter. Because NA64 has been approved and funded to search for dark holes. Period. Nothing else. They will not produce other papers which are now related to dark hole. Anything else, they won't produce. So that's why we come in to do other things. This is relatively easy, I think, because it's just not letting expressions. Okay. All right.
Okay.
All right, thanks, guys.
Thank you.